Hey everyone, I'm Jared, and I am indeed here to talk about some lunar terramechanics work we've been doing at the Center for Lunar and Asteroid Surface Science at UCF. I think the last four talks did cover, honestly, most of what I have in here pretty well, but I hope to provide some new insights and equipment that are of service to the community. So, as we know, to live sustainably on the lunar and other planetary surfaces, we need to develop reliable mobility capabilities. This is really tricky due to reduced gravity, lack of atmosphere, and challenging physical properties of the regolith itself. So we actually need to do experimental work here on Earth to test rover wheels, their designs, operational modes in terms of speed, acceleration, deceleration profiles, required torque for efficient operations. But experimental work is not enough in this case to inform future missions. We do also need to do computational predictive work to actually estimate how efficient we are on driving, as well as dust plume trajectories and more. For these computational methods, as Joseph did a really good job of outlining that took away a couple of minutes of my slides later, you do need to calibrate the material properties of these models for accurate simulation. So on the experimental side, we've developed RIDER. It's a regolith interactions for the development of extraterrestrial rovers bin, full-scale planetary testing rig. The simulant bin you can see in the bottom with the lights on the picture on the right-hand side here. It's just shy of 4 meters long by just shy of 1 meter wide with about half a meter deep simulant bin. It is housed in the UCF class Exolith lab, so we have access to world-class simulant production facilities and dust management capabilities. Specifically, RIDER has a gravity offload or load application system where we can actually control the load we put on each wheel, such as in the top right, you see a Viper-like resource prospector wheel that we had loaned to us. And we, based on the mass of each rover wheel we test, or well, the mass of the rover that each wheel is for, the gravitational acceleration of the target body and the number of wheels, we can prescribe a certain load to the wheel and maintain it as we travel across the bin. Since rover wheels at this point are frankly not standardized hardware, we had to come up with a way to couple each unique wheel to our motor box. So we manufacture adapters to go from our wheel hub that you see on the motor box on the top left to couple to each wheel. Within that motor box, I should note that this is a towed wheel system, this is a driven wheel system, not a towed wheel system. A lot of wheel rigs like this end up powering the rail and gantry system from above and kind of pull the wheel along, but that's not how rovers work. They have direct drive trains to the wheels. So we developed our dust-proof motor box and have interchangeable programmable brushless DC motors. They all have the same NEMA form factor, so we can just pop open the box, swap them out. And they do have different gear ratios, so we can actually test different speed and torque ranges and how they affect wheel efficiency, trafficability on the regolith, and so on. And to continue on with some of Mike Lucas's points on simulant compaction, we actually did work with him and Clive to expand that study to RIDER, where on the bottom left, you can see one of our students ready and willing to shovel in 2.5 metric tons of high fidelity Lunar Island simulant into the bin, place compaction surcharge boards with vibration motors on them, and compact the simulant. As far as I know, this is the largest simulant compaction experiment to at least a specific set of densities that I know of. If I'm wrong, please correct me, but I thought that was kind of cool when we thought about it. And as Brandon has so eloquently pointed out, moisture content does indeed affect physical properties of regolith and its simulants. So in RIDER, in the top left there, or in the top picture in the middle, we have a blue box. That's our dehumidifier. It's a bit of an effort to pump out all the moisture in the air in Florida in May, June, July, but we're doing our best and actually getting pretty good results for what it's worth. The two black boxes on the left with orange writing are air filters that also provide negative pressure to help keep dust in the bin while we're operating. The bottom right picture is one of our HD video cameras that we use to image the wheel as it rolls around from multiple angles. And our control and data logging system actually does live outputs of parameters like motor current, program speed, load being applied to the wheel, and so on, and also logs these data to comma delimited ASCII text files for later use. I did mention we had a Viper-like resource prospector wheel, but we also were loaned from NASA Glenn an LRV replica wheel, one of 12 in the world. Huge honor to be able to work with this wheel. I wanted to include this video of us actually rolling the wheel back and forth a bit. This was part of a testing campaign as part of class with the University of Notre Dame, where we tested an Astrobotic Polaris prototype wheel, this LRV replica, as well as the Viper-like resource prospector wheel to compare the efficiency of travel, the particle size and shape evolution under the wheel, as well as cone penetrometer resistance inside the wheel track and outside the wheel track to see if density subsurface evolves as we drive back and forth hundreds of times. And blazing right on through to the other half of this, how we're studying terramechanics computationally. SPIDR, it's our simulator for planetary interactions with dust and regolith. It's a discrete element modeling simulation for rover wheel interactions. We can take in CAD-based wheel geometry, such as the LRV wheel and fender shown here, prescribe certain gravity based on the target body we're after. Right now, we have the LRV wheel in there, so we're simulating the moon. We also have charged particles and electric fields in the vacuum environment of space. Overall, SPIDR provides us with information on, like I said, wheel efficiency, but also enables us to predict dust plume trajectories and velocities, which is a really big deal because when we're doing donuts on the lunar surface, like we all want to do, we want to be careful not to sandblast our own equipment or worse, our lunar neighbors' equipment. I'll skip over a little bit of detail on the calibration here since Joseph did such a good job on that, but we did angle of repose studies for our collection for our calibration data as well. We did column collapse angle of repose experiments using Lunar Mare and Highland's Apollo samples, and I'll give due credit for that in a minute. But we run these experiments, record them, and also we do include Exolith Labs LHS1 and LMS1 simulants as comparison here. But we run these column collapse experiments. We measure the width of the column at various stages of lifting. The cylinder funnel is lifted at a constant velocity, and we have the videos timestamped so we actually know at what stage of the experiment we're in. Then we take the DEM, replicate the experiment in the DEM, same amount of sample mass, same cylinder width, same lifting rate, etc. And we iterate over parameters of values for the parameters of sliding friction, rolling friction, and cohesive energy density, a cohesion related term. We do use the Lights open source DEM package for this. And once we have the values that are our best fit for these experiments, we plug that into our wheel simulations and off we go. I'm getting a bit short on time here, so to wrap it up, we at class are trying to acknowledge that, no, we can't just look at things in terms of experiment or theory. We're trying to study at the intersection of those. We're also trying to study terramechanics at the intersection of regolith and rover design. And RIDER and SPIDR are our stabs at this. I should also note that these facilities, virtual and physical, are available for community use to the lunar science and engineering communities. We're happy to collaborate with you to get your wheels in RIDER, to get your wheels in SPIDR, and help answer key science and engineering questions to help us live sustainably on the lunar surface. Again, I'd like to thank the class Survey Node PI Brit at UCF in collaboration with Clive Neal and Mike Lucas at the University of Notre Dame. For the RIDER team, I'd like to thank Colin Krieger at NASA Glenn Research Center for loaning us the LRV Replica and Viper-like resource prospector wheels, as well as Mike Provenzano at Astrobotic for the Polaris prototype wheel loan. For the SPIDR teams, special thanks to Dr. Carrie Donaldson-Hanna and the rest of the Thermal Infrared Emission Spectroscopy Lunar Sample Characterization Consortium for collaborating with us to provide Apollo samples. It was much, much appreciated. It was an honor to work with those samples. Also, thank you to Ron Creel for providing us with the LRV wheel and fender CAD files and the related information to, I'm sorry about this, get the wheel rolling in our simulations.